So in this video, I just wanted to walk through a typical workflow for amateur spectroscopy, and specifically slitless amateur spectroscopy. I've been collecting lots of bits and pieces of information over the last months, and I didn't see a lot of sources where I could just go and get a full A to Z story on that yet. This may be a little bit of a niche hobby right now, and I'm quite surprised that not more people are picking this up, given how easy it is today. So I'm focusing on just slitless amateur spectroscopy. And that means that in many cases people are just using a star analyzer grating that you can get from different suppliers. So the grating is blazed, that is very important. So it is more sensitive in one direction than the other. And it has a diffraction pattern, so it breaks the light, almost like a prism. And they put this into these nice holders, so you can put it into a filter wheel. Very easy to integrate with your equipment. Resolution is limited, so typically between 50 and 100. You can use the equipment that you have. So here's my rig. It's a typical wide field AP rig. Harmonic drive for tracking, a Mealy computer with Nina on it. And I can also run SharpCap on that Mealy computer. Then I have a mono camera, a RedCat 51, so that's a 250mm focal length, 51 millimeter diameter telescope. And then I have guiding with a guide camera and so forth. So this little grating goes between the telescope and the camera. So this is a convergent beam setup. And then the nice thing is that you can use free software. Now SharpCap has a license of $18 per year for the Pro Edition. I would highly recommend that. They have a free version as well with some ads, which is still absolutely worth using. The other packages are all absolutely free. SIRIL, very powerful program for stacking, and also image enhancement for astrophotography is free. ImageJ, a very nifty small program that does exactly what you need, is also free. And then BAS Spectro or BAS Project is free as well. And it is such an amazing piece of software that I mentioned it twice on this slide. After you've bought that diffraction grating and some adapters, you can use your existing AP equipment and free software to actually do spectroscopy on stars and planets and whatnot. Talking about that workflow. So this is that typical workflow. You start with planning your objects, then you spend your night, your evening on acquisition, and then typically the next day you start with the data processing, the stacking, the data reduction and analysis, and then you get to publication. So at the end of a night out, you have a lot of pictures with stars and rainbows, those diffraction patterns. In this case you see here a picture with a color camera. And you have to process all that data before you can get it to the next steps for analysis. So at the left hand side you have those images. And you want to end up with this picture on the right hand side. So this is a spectrum, a 1D spectrum of Sirius, a star. And on the x-axis you see the wavelength, so the frequency. And then on the y-axis you see the intensity. So you're typically interested in the features, but then also in the general shape of this curve that is called the continuum. Now, publication means different things to different people. Some people upload their results into a pro-amateur database so that they can support scientific advancement. Other people, they publish this on Instagram or Facebook or whatnot. The steps of that workflow, right? So one step that I'm going to discuss today is the acquisition. How do you find the right settings for your gain and your exposure time? And how do you collect data efficiently? And I'm going to use SharpCap to demonstrate that. The next step is around stacking. So here I improve the signal to noise ratio, and I am able to reject the bad subs if there are any. And I'm going to use SIRIL for that. You can find SIRIL at that webpage there. Then data reduction. So how do we get from the pixels to the wavelengths? That's called calibration. And how do we correct for the instrument response? How do we determine resolution? These are all addressed in this data reduction step. And I'm going to use Spectro, BAS project for this, which can be found at that link. And then the analysis can also be done in BAS Spectro. So looking at absorption, emission lines, we can estimate the temperature of the surface of the star. If there's a galaxy, you could look at red or blue shift, see if the galaxy is coming towards us or drifting away from us, etc., etc. So let's get started with that acquisition. Now, a couple of gotchas when you do spectra. One is that the focus is very important to get right, and the other one is that you want to prevent overexposure of your diffraction pattern. So there's not a very good way in SharpCap to look for that today, but I found this small program called ImageJ, which is also a free program. Here we have, for example, one sub. So I do that before I start generating the SIRIL file. And I can look at the ADU values, at the gray values of this selected region. So go to Analyze, Plot Profile. The star is the brightest object, so this is close to my maximum ADU value for my CMOS sensor. But the data that I'm actually interested in is not yet clipping. So this is not overexposed at this point in time. So it would be helpful to increase the gain a little bit, or in this case increase the exposure time a little bit, so I can get a better signal to noise ratio. There's not a lot of noise in this particular frame, but it will definitely help a little bit. The other feature to look for is focus, right? So don't focus on the star, right? Tune your focus for your telescope so that the features from your diffraction pattern are as clearly visible as possible. So basically you're looking for deep features, deep and sharp features. So this could use a little bit of focus adjustment. I think I can get a little bit sharper here. But it is not completely the same across the whole spectrum. There's the effect of field curvature. So if I have my spectrum very, very focused in this blue area, then it's not very, very focused on the red area, and the other way around. So I have to compromise a little bit, or just focus on the region that I'm mostly interested in. So those two aspects, like preventing overexposure and making sure that you get the right focus, those are important to set up before you start with the massive data collection in the SIRIL file. So now that I know that my exposure is right and my gain is right, then I can start with the data collection. So be careful that this box auto is not on, so that you're able to select the output format that you're interested in. Of course, you could do individual frames that would save an individual file, but if you select SIRIL file, then basically you get one bundle of raw files. It's almost like a video file where you have like one file, and on each frame is a raw of your subs, basically, of your experiment. So then I'll just go to capture, start capture, put in my target name, and then the couple of frames that I would like to acquire. And then I click on start. So now it just makes all these frames, saves that file into that place that you have indicated. And there you go. Okay, so how do I stack with SIRIL? Very simple, I'll demonstrate that. First very step is to set the home directory. So I have this set up here. And then I open up the SER file. You see here this file has 200 frames. It's a mono cam, so it's ASI 533mm Pro. And it's about 3 gigabytes. You see here that I have like the full frame of the camera, so I didn't select the region of interest. I don't have to debayer because it's a mono, so there you go, I open it. I'm going to skip over calibration, but here's where you usually would plug in your master dark that matches the temperature that you've set this to. So this is a cooled camera, so I would match that temperature. So you can do a registration. There are basically two options. you can go for a global star alignment, which is the default for astrophotography. And in this case, that will be sufficient because there are plenty of stars kind of hidden a little bit in this picture that the program would be able to pick up. If you want to do just stacking with one star, then there's a little bit of a trick to it. So you select 1, 2, 3 stars. You then select the star that you're interested in, pick first star, and then it would provide you a shift only registration. So it would only transform in X and Y and would not compensate for rotation. So that is a thing that you could do. So then I would just click go register and it would machine away. So you see that 200 frames are now registered. It took about 4 seconds to go do that. Here's a plot of the cumulative error and your star size over time, which is looking pretty healthy. You're then ready to go for stacking. So I choose average stacking with rejection, and I set it to no normalization. And then I start stacking. So successfully completed, and it opened up this stacked fit file, which is now also available in this directory. So you can open up your image straight away in Best Project to get it ready for data reduction. So here I open up that big image. But I have to rotate this first and make it ready, crop it out to get it ready. So first flip the image to the right. So now at least it's oriented from blue to red. Then I can crop the image all within the same tool. And then I can also fine adjust the rotation because the rotation is just off at almost 1 degree. So image, rotate, correction, draw angle here. And then I basically draw a line from the 0 order. And it only looks at the angle over the diffraction pattern. And now it corrected for the angles. Now it's really horizontal in the view. So very first thing that I do is to select the binning region. So that's the region that you use to calculate your spectrum from. And I want to choose it relatively narrow. So I go here and set active binning region. And then I also want to set the sub-region, so that's the other regions. And it's used to subtract the background. I can then go to region selection tool and then further tweak those regions. So I can, for example, make this region a little bit bigger by making this selection here a little bit thicker. So that means that I, on this side, walk up the number of pixels. I save it. And I can go to region 2. There I just want to start a little bit earlier so that I select more. So this number needs to go down. And I want to get it relatively tight next to the binning region. So next up is calibration. So click on this button and then you see this pointer with a circle on it. You can drag this over the first area and we'll just take the maximum or the minimum of that feature. So here it's determined that the peak is at 36 pixels and that's my wavelength number 0. I can add another point, for example here, and I know that this point is probably the H alpha, beta, well, could it, comma, add another point for beta, add another point for H alpha. And then here you can choose how you want to do this kind of scaling from pixels to wavelength. Now there's a little bit of nonlinearity in these gratings, so I'm not going to use a linear, I'm going to use a quadratic, and then I'll finish my calibration. To verify that I go to the element lines and I choose the same element, so hydrogen, and then I select a bunch of those to be added to my picture. And of course you would expect that those three are exactly at that same spot. But the good news is that the other ones are also very well fitting my plot. So I go to crop axis range. I always prefer to work in nanometers. And there you go. So this is the calibrated, not instrument response corrected picture of Sirius. Move the legend up and you can add some titles and stuff. So Sirius, you can do your data here. There you go. Okay. So next up is to subtract the instrument response from this picture. So let's just Google what the spectral class is for Sirius. And it is an A15 class spectrum. So I go to my star library, my reference library, A1, and there's no A1. But there's a A1045, and there's a 2, and they're like almost the same. They're almost the same. You can take the average. I just chose to pick one. So here you have the reference spectrum, and the blue one is what I measured. So the difference is all the atmospheric aberrations that you get, so that's probably in this upper region here, but then also my quantum efficiency of my camera. So in order to divide out my instrument response, I go to Math, divide profiles, and divide my captured data from the reference spectrum. And it's a little bit hard to see here because I have so many lines on. Let me try and turn those off. But you see here, the blue spectrum is my data. This is the reference, and this looks very closely to the quantum efficiency of my camera. So here you see the quantum efficiency of my camera, and it has this kind of slope and a little bit of scribbles here. So you would expect this. So next up is to fit the curve through this rather noisy difference and use that curve to compensate my data. So you can fit this continuum. You select your target profile, so that's on the residual. And then here with double clicking, I just take roughly the values of my instrument response. I want to save this as a separate .dat file. And then I can close these images. I don't have to save them. And then I can go to my original data, go to Profile Properties, Response, Response File, and then I can select my instrument response. And it will now automatically compensate for my instrument response. So here you see my experiment, the blue one, with the high resolution reference spectrum in green. And of course my resolution is not as good as what you find in the library. But the features are kind of the same, and the continuum is also fitted out pretty well. Here you see some atmospheric aberrations, but you clearly see the H alpha, the Balmer lines here in the A1 spectral class star series. So that's good news. Now, what about resolution, right? So if I want to understand my resolution, this is a star analyzer 100. So the resolution should be in the range of 50 to 100. And similar is resolving power. It's kind of the same as resolution. There are a couple of tools here that are super helpful. So for example, you could select here a range, and it will calculate the depth of your features. You can run this, and then your measurement results will give you the resolution. So here you see that this experiment was had a very good resolution at close to 100 at this this specific frequency. I could do the same on other values. Run this, and it would show slightly less, but still pretty good, right? If I look at this feature here and run this, it actually shows 120. That seems a little bit optimistic to me, but still pretty good. So one more thing that is nice to do is to normalize the spectrum. So that basically means you scale the y-axis so that it crosses 1 at a specific frequency. And I usually want to scale that exactly around green area. So here you see that right now at 555, it's close to unity. So now we have our spectrum calibrated for wavelength and adjusted for instrument response. So we can further tweak how we want to display this with the properties of the chart and so forth. A couple of cool things are that you can show a color, synthesized color image strip here. So it shows you kind of the rainbow that is generated from matching the colors with the wavelengths of your spectrum. You can go wild and do the same thing to the background of the chart, like so. You go to colors and then wavelength color blend, and it would show you exactly the colors matching the frequencies as a background. But there is also some more scientific stuff that you could do. First of all, you can label the elements. Right, so this is a A1 class star, so it has very sharp features, these Balmer lines. And we've showed that before during the calibration. But you can easily throw them in, right? Hydrogen, select H alpha to wherever you want to go. And then add them to the chart. And they are, of course, matching exactly the features that we've used for calibration as well. So the other thing that we can do is to estimate the atmospheric temperature of the star using the Planck curve tool. So the Planck curve, the curvature itself, is determined by the frequency that matches the peak of the intensity of your spectrum. Now for an A1 class type star, that peak is far to the left here. So it's below the 275 or so that we have collected in our spectrum. So it's outside of the range. So I have to do a little bit of tweaking with the wavelength to get the curvature right. Then the two other parameters that you can do is changing the height and the offset. So you got to tweak a little bit with these degrees of freedom to get that curvature match your spectrum. And once you have that, then you can read of the temperature that you estimate the atmosphere to have of this star. So I do a little bit of tweaking here to get that right. And then basically you see that this curvature is actually really well fitting my spectrum. And then the temperature that I would estimate is about 18,000 kelvins. So I can save that, and that curve is now shown in the legend of my chart. So now we have completed our amateur spectroscopy workflow from acquisition, stacking, data reduction and analysis. We have now arrived at this one-dimensional spectrum of series. We have used the following software along the way: SharpCap for the acquisition, ImageJ for some cross-checks and setup for the acquisition, SIRIL for stacking, and then BAS Spectro project for data reduction and the analysis. Let me know if this was useful. Go shoot some stars and clear skies.